Hello, this is AMAT 104 lecture recording, week 9.3. So up until last class, we looked at chapter 16.1 about the sample space, random experiments and events. And using that background knowledge, today we're going to go over chapter 16.2, and that's the multiplication rule, permutations, and combinations. So 16.2. The multiplication rule, permutations, and combinations. So some of you have already learned the permutations and combinations, and today we're basically just going to go over the definitions, formulas, and very simple examples. So before we do anything, let's start with the definition. So counting. So this chapter is all about counting. Remember last class we learned about the sample size, and this is something similar to that. So let's say counting is the process of determining the number of elements in a set. Okay, so that was pretty simple. That's just meaning counting. And here's the multiplication rule. So if there are m, so this is a number, m, different ways to do x. X is an event, and n different ways to do y, then x and y together and in that order can be done in m multiplied by n ways, different ways. So I know that this definition is very wordy, but it may make more sense in context. So let's actually do an example regarding multiplication rule. So let's do an ice cream example. So let's say there are let me quickly. So let's suppose that your local ice cream parlor offers two different choices of cones. And three different flavors of ice cream. Then we can see, so here the problem is, how many different ways can you order ice cream from this shop? It's actually quite simple because we have two different cones. So the choice of cones, you have two. And for the choice of flavors, you have three. So simply, let's actually draw a table for easier description. So let's say for the cones, so here are the cones. Let's say they have a cone that's pointy. I'm not a very good drawer, but let's say that's a pointy cone. And let's say there is a cone that's a little more like a McDonald's ice cream cone. Let's say there are two different cones. And for the flavors, let's say there is a chocolate, strawberry, and vanilla. Then you can see, you can have in this pointy cone, you can have chocolate and strawberry and vanilla. And also in this McDonald's style cone, you can also have three different flavors as well. So you can see that we have 1, 2, 3, 4, 5, 6 different cones. I mean, 6 different choices. So I wish I could draw all these pictures, but let's save some time. So as we can see from above, let's say, using multiplication rule, we can conclude that there are 2 multiplied by 3, which is 6 different choices. For a single order, but let's say that. Now let's look at the same example. Let's actually say that it's the same type of deal, but instead, let's change up some numbers. So in this case, we only had 3 choices of flavors and 2 different choices of cones. So it wasn't hard to just draw a picture like this and see how many there are. We just counted how many there can be. But what if the numbers are a little bigger? So let's look at an example. So as we can see from here, we only have to do 2 and also multiply by 3. And as we can see from this table, the multiplication rule, in this case 2 multiplied by 3 is 6, and it came out just like that. So keeping that in mind, we're going to do an example with bigger numbers. So it's harder to draw a table like that. So let's say this is episode 2. So suppose now there are 5 different choices of cones. and let's say 31 different flavors of ice cream. So as you can see, yes, we can proceed to solve this problem like how we did here. We could just draw the table and draw a 5 by 31 table, but that's also going to be very time consuming and would not be very efficient. But as we know, by multiplication rule, let me write everything down. So from actually, that's actually not so. So we have 5 cones. And for each cone, we have 31 flavors. So simply, we have 155, and this is actually from 5 multiply 31 choices. So different ways to order. This, yeah, that's it. It's simply by multiplication rule. Now actually add in one more scenario. So I'm going to keep the same scenario as a second. So let's say now we have 5 cones and 31 flavors. And now you have 8 more toppings. So we added another dimension in there. So we still have 5 different choices of cones, and we still have 31 different choices of flavors. But instead, we now have another variable, and it's the toppings. And suppose that you are ordering one of each. So to order a single serve ice cream, let's say you have to get 1 cone, 1 flavor, and 1 topping. Then how should you do it? It's actually quite simple. It should actually be the same way. So by multiplication rule, we have 5 multiplied by 31 multiplied by 8, and that should be 1,240 different ways to order. So that was quite simple, and I think we all understand the multiplication rule as is already. So let's now look at something different. Let's say a new example. There's a horse, so suppose this pad is a little finicky lately, so it's acting up a little bit. Suppose, okay, perfect. So suppose 10 horses entered in the race. And let's say if the first, second, and third place was awarded, how many different outcomes can there be? So how should we approach this problem? So this is actually a little bit different from the ice cream example where we have different choices, but it actually isn't too different. So let's actually think about it that way. Let's think about it and let's divide it into different places. So let's say for the first place, so how many choices or how many different ways can a horse come in the first place? I know that's a very weird wording, but as we can see, so let's say we name the horse by number. So let's say there's a horse number 1, horse number 2, horse number 3, and so on. So if that's the case, for the first place, we have 10 different horses. That can come into first place because there are 10 horses and each one of them can win, and I'm sure that makes enough sense. So let's leave it as that. And now let's go on to the second place. In the second place, so second place always comes next to, after the first place is decided. You cannot choose the second place before the first place. So out of these 10 horses, one of the horses came first. So they already are in the first place. So for the second place, now we have 9 different horses because one is chosen to be the first one. So and this is because the these are the remainings after the first place. And I hope that makes sense. And we can actually, if you understood that, the third place should be simple enough. So third place cannot come, so it can only be decided after the first and second places are decided. So we have one choice for the first place, and we also have one choice for the second place. Now, after the second places are decided, we now have 8 remaining horses, so 8 different horses. And that's it. So out of all the horses that entered this race, each one of them could win the first place. But after the first is decided, the remaining 9 could potentially be the second place. And also after the second place is decided, the remaining 8 could possibly be the third place. And that's actually it. So we can simply say that we have 10 multiplied by 9 multiplied by 8. So it's 720 different outcomes. Does that make sense? So here, I'm going to define a couple things. So this chapter includes the permutation and combination, but we really haven't defined what each of them are. So each of them is. So let's say permutation is simply unordered, and this is a very important word. Order is very important. Selection of R objects. So R is a number chosen from a set of N is also a number objects. And obviously here R is obviously smaller than or equal to N. And in the special case, where R equals to N, all objects are selected. And the permutation is just a rearrangement of the objects. And simply the notation goes as such. So the notation and the formula. So when we say NPR, so these are subscripts. The P is a capital P and they're subscripts of N and R next to each other. And it's simply given as N multiplied by N minus 1 multiplied by N minus 2. And you're simply multiplying all the way down to N minus R plus 1. And that's simply N factorial divided by N minus R factorial. Here, this exclamation mark is called factorial. And means that N factorial, it's simply N multiplied by N minus 1 multiplied by N minus 2 multiplied by all the way down to multiplied by 2 multiplied by 1. And that's what the factorial is. And we read this N factorial. So I know this is a little too complicated, and oftentimes, so really all you really have to understand here is what this means. So if you understand this notation is for the permutation, and this implies that different number of ways to choose and order R out of N objects is expressed as this, and it's a permutation. And that's all you really need to know. And this is the factorial notation, exclamation mark, and this is what this is. So if you go on to, so here's a note for all of you, so that NPR, it's a function, is available on scientific calculators. And the access may differ, so may vary by calculators. But is usually under math function or probability function. Hope that makes sense. So in this horse example, let's actually use this horse example to use with this simple permutation. So we know that in the horse example, we have 10 different horses. And we are interested in ordering 3 different horses. Does that make sense? So that implies that the whole calculation is 10 permutation 3. And simply, we can say using this formula, it's 10 factorial divided by 10 minus 7 factorial. 7 factorial here. And we know that 10, so 10 factorial, let's leave it as that. And 10 minus 7 is 3. So it's going to be 3 factorial. No, sorry, why 7? Let me redo this. So 10 permutation 3 is given by 10 factorial divided by 10 minus 3 factorial. I don't know why I wrote 7. And simply, let's leave the top as 10 factorial, and let's calculate the bottom. So 10 minus 3 is 7, so it's 7 factorial. And by definition, we know that 10 factorial is given as 10 multiplied by 9 multiplied by 8, 7, 6, 5, 4, 3, 2, and 1. And in the bottom, we have 7 factorial is 7, 6, 5, 4, 3, 2, 1. And simply, you can cancel the same numbers. 2, 2, 3, 3, 4, 4, 5. Gotta do something about this pad. 4, 5, 6, 6, 7, and 7. And we're actually left with 10 multiplied by 9 multiplied by 8. And that is the same thing as 720, which is what we actually had here. So in reality, in all these problems that we will encounter in this course, we'll not really use all these elaborate calculations, but this is if you understand this, it'll make this course a lot easier for you. But you will be given small enough numbers so you can actually hand calculate this like we did here. Okay, so the next definition is combination. Combination. So this is the same thing, but this is unordered. So here, this is important. It's just a collection instead of order. Selection of our objects. Chosen from an object. And the notation goes NCR. So this basically denotes the number of choices of R combinations out of N objects. And simply, this is the same thing as NPR divided by R factorial. And that is N factorial divided by R factorial multiplied by N minus R factorial. And similarly, can be found in the calculator under the same place as the permutation. Calculator. Okay, so those are the main definitions that I wanted to go over. For the factorial, you'll be using this a lot. So let's actually do some examples with the factorial. So examples, factorial. So factorial, so n factorial, I have defined it as to be n multiplied by n minus 1 multiplied by n minus 2 all the way down to 1. But if you put that into practice, let's say 2 factorial is simply 2 multiplied by 1, and that's just 2. That's it. Similarly, if you say 3 factorial, it's 3 multiplied by 2 multiplied by 1, and that is 6. And if you say 4 factorial, it's 4 multiplied by 3, 2, and 1, and that is 24. And we can keep the same pattern. So given any number, you can just do this. Or if the number is too big, you can also find this in calculator. On calculators. Let's now do another example, and let's actually expand on the ice cream example. So ice cream, and is it episode 3? So suppose an ice cream parlor offers 31 different flavors. And one of the special, let's say, is the, let's say, true double. And this is simply 2 scoops of different flavors in a bowl. So the question is the same. So how many different ways can you order the true double? So here we actually took out the cone or the toppings. So we only have 31 flavors and it's served in a bowl. So we don't really have to think about the other variables. So we have 31 flavors and we're choosing 2 different flavors out of 31. So how would you approach this problem? So let's actually go solve this problem in 2 different ways. So simply we can say there are by, so this is, let's say, the first way of solving this. So by multiplication rule, there are, you can choose 31 for the first flavor and you can choose 30 for the second flavor. And naturally, you may think that 930 flavors is correct, but is it really correct? So here is a big flaw. So when we're using the multiplication rule, there's a well-defined order to things. So what I'm saying is that, so suppose you chose chocolate and vanilla. In this number, it's actually considering and the vanilla and chocolate are the same thing. I mean, are not the same thing. So it's actually counting it twice. So simply now we have to consider another thing that obviously for some people being served chocolate and vanilla and chocolate are not the same thing. But let's suppose for the sake of the problem that they are the same thing. So we should here understand that the number 930 is not correct. So this is wrong because there is an order to things. And in this case, they are not looking at this order as the same thing in reality, but it is. So all we have to do to get the correct answer is to divide the original count by 2. And this is because there are 2 different ways to serve two different flavors of ice cream. In other words, we have chocolate and vanilla, or vanilla and chocolate. And this is all it's saying. So we have 1 and 2 different ways to order the 2 different flavors of ice cream. So simply what we're doing is the 31 multiplied by 30, and you divide it by 2. And that is 930 divided by 2. And that is 465 ways. And this is the correct answer. So let's actually now solve the same problem using the combination that we just did. So second way of solving it is simply, you can say 31 combination 2. It's the same thing. And simply this is 31 factorial divided by 2 factorial multiplied by 31 minus 2 factorial. And this is simply saying 31 multiplied by 30 multiplied by 29 multiplied by all the way down to 1 divided by 2 factorial is 2 multiplied by 1. And you multiply that by, this is 29. So it's going to be 29 multiplied by 28 multiplied by all the way down to 1. And as we can see, all these numbers from 28 down will cancel out. So you will end up with 31 multiplied by 30 divided by 2. And simply that is 465 we have found before. So I guess I just wanted to show you that these two are the same way. You can either choose to go about using this formula or just plug it into the calculator to get this number, or you can use the deductive reasoning to get to the number that we need to find. I personally think the second option is a lot quicker, but for some of you, it may be easier to just go step by step and think about it deductively. Now let's look at one more example now. So one last example before I let you go. So, and this is probably going to be the last ice cream problem. And this is episode 4. So now suppose you have the same thing. So you have 31 flavors. And you are choosing 3 different flavors in a bowl. And in this case, also the order doesn't matter. Let's say the order doesn't matter. So how would we go about solving this problem? So for this specific problem, if we were in-person meeting, I would actually let the students decide, and there are usually a couple different ideas, and we can have a small little discussion about it. But so here are the few ideas that often comes up in the class meetings. So we can clearly see that there are 3 ice creams and with 3 different flavors they have to choose from 31. So naturally we have 31 multiplied by 30 multiplied by 29, which is 26,970 different choices. But we know that this is not correct. Because in the previous example with the episode 3, we learned that this number does not take the, it does take care of the order, but in this case, the order does not matter. So this actually includes all different combinations, but with the same flavors as well. So how would we eliminate it? So in the previous problem, we simply divided by 2. So among different opinions of students, there are a lot of students who argue that it should be 2 because that's what we did before. And some students say it should be divided by 3 because when there were 2 flavors, we divided by 2. So when there are 3 flavors, we should divide by 3. But both of the ideas are not correct. So here is the idea. So suppose 3 flavors, and in this case, let's say strawberry, chocolate, and vanilla. And if we were to order the 3, it means that we can have either chocolate, vanilla, strawberry, vanilla, and chocolate, and those 2 are the same thing. And we can have chocolate, strawberry, vanilla, chocolate, vanilla, strawberry, and we can also have vanilla, strawberry, chocolate, vanilla, chocolate, strawberry. So here, suppose you're choosing strawberry, chocolate, and vanilla flavors, and all of these 6 options that we have, they are in fact the same options. They are the same combinations of ice cream. So in reality, we actually have to, so there are 6 ways to order 3 flavors. So simply, we have to divide the 31 multiplied by 30 multiplied by 29 by 6, because we're simply eliminating all this possible ordering issues by doing so. And if you put this into the calculator, obviously the top we have calculated here above, it's 26,970 divided by 6, and that's actually going to be 4,495 ways. And you should simply be able to get this simple number by plugging it into this combination formula. So all that's really important is to make sure first how many of options there are and how many we're choosing, and if it's ordered or not ordered. That's all we're really doing here. If it is not ordered, like in this example, we're using the combination formula. If it is ordered, then we're going on to the permutation formula, just like the horse example. But if you decide to go with deductions like this, it will be really hard to figure out how many there are like this. So obviously with the 2 ice cream, we can either get the chocolate vanilla or vanilla chocolate. So there are only 2 options. But when there are 3 flavors, we already have 6 different ways. And what about there are 4 flavors, 5 flavors, 6 flavors? It's going to be a lot harder to keep track on those things. But we should be able to see that this is simply ordering 3 different objects. So this number is actually found by 3 factorial, which is 3 multiplied by 2 multiplied by 1, just like the horse example. So it's 6. So the whole point of why I'm mentioning this is that if you decide to go with the deduction method, so if to solve these problems by deduction, and if the order does not matter, in other words, this is combination, you have to divide the multiplication rule by r factorial, meaning that how many different options that you're choosing. So for example, for the previous example here, we divided by 2, and that's actually 2 factorial. So 2 here is 2 factorial. And 3 is 3 factorial, which is 6. And lastly, if you were to given the same problem, but now you have 4 different choices, it'll be very hard to label out everything. So simply you can, so if given the same problem, with 4 different flavors, you would be doing 31 multiplied by 30 multiplied by 29 multiplied by 28, and that's the multiplication rule part, and you would divide by 4 factorial, which is 4 times 3 times 2 times 1. So I think that's all I'm going to say for today. I know it was a lot to take in terms of the permutation and combination especially. So next class, so I think week 10.1, I am mainly going to spend the entire class going over different examples that you might encounter. And all the examples are actually directly from the book or the homework problems as well. So if you practice all those problems and master how to solve all of them, it should simply be what you should be expecting from this class. So thank you for joining the class, and I hope you have a great rest of the day.